Can people? Okay, let's see. Is that now too loud? Yes, it is. Okay, let's try it now. Can people hear me in the back? I trust you can. Okay, let's start things off. First of all, are there any technical questions or logistical questions from anything we've done? You should have the third homework assignment if you want to start working on graph stuff over break. If not, have break. Any questions about what we've been doing? We're talking about graphs. We talked about breadth first search last class. Any questions? Okay, one thing I did not cover on breadth first search. Let me try this. Is this better? Can people hear me in the back over the mic still? Okay, let's try this, and let's say this is probably better. Okay, so we've been talking about breadth first search in graphs. And what is important to know about breadth first search? It is important. It's good to understand how it works. You should really be convinced you understand how the algorithm for it and depth first search work, okay? Because there are subtlety there. But basic principle with breadth first search: you started in one place, you radiated out, visiting vertices at first a distance 1 away, then 2 away, then keep radiating out in terms of the number of hops from the center. What makes traversal interesting and useful is that you can do things when you are visiting the edges and vertices. Okay, so breadth first search by itself is not a thing you want an algorithm for. You want an algorithm to use breadth first search as a subpart of it. And one, let's say, simple application of breadth first search, which I want to illustrate here, is that of two-coloring a graph. When we talk about coloring a graph, we'd like to take the, here we have a graph. There's vertices, and there are 5 vertices and 5 edges. You see, they form a nice little loop. We say that a coloring of a graph is an assignment of the vertices to colors, okay, such that every edge touches different colored vertices, okay? So in this particular case, we could color this vertex red and this vertex blue, and now that edge is on different sides of different colors. If we color this one red and this one blue, all of these edges are happy now. What color can we color this remaining vertex so that it is, you can color it green. You could color it green, except all I've got is black. Okay, so I can only color it black. Okay, but you get the basic principle here, that for this particular graph, in order to make sure that every vertex gets, you color each vertex so that every edge is on 2 adjacent colors, is on 2 different colors, you need 3 colors for this thing. If I want to color an n-vertex graph, how many colors do I know that I can get away with? If I have an n-vertex graph, how many colors can I get away with if I don't care about how many colors I use? N. If I colored every vertex a different color, then every edge is going to be incident on 2 different colors. Does everybody get that idea? The hard thing is finding the smallest number of colors. Okay, and as we'll see when we get to NP completeness, it is in fact a very hard thing. But there are a lot of graph problems that come up in scheduling, in optimization, where finding what's the smallest number of colors you need in a graph turns out to be interesting. And the special case where you can get away with 2 colors is actually quite interesting. It's a question of a graph. We say a graph is bipartite if it can be colored without any conflicts using only 2 colors. Okay? And the reason bipartite, there's 2 reasons why bipartite graphs are very important. One is, on one sense, is that they come up a lot. A lot of graphs in the world are built up of 2 different kinds of things. Boys and girls are 2 different kinds of things. Students and the courses they take are 2 different kinds of things. We could imagine a graph where One set of vertices are the people, the students in the class. Another vertex is a course, every course that you are taking now, that is being offered. You could imagine there being edges between students who are taking a class. This student is taking those two classes. This student is taking these two classes. This student isn't taking anything, may have dropped out. That student's taking one class. Does everybody see we can build a graph, for example, naturally between students and the classes that they're in? And that is naturally, by its application, by its definition, going to be a bipartite class. No student can take another student. No class can take a class, right? Only a student can take a class. And if you believe that, that naturally defines a graph with two parts to it. Two parts, bipartite. Any questions about that? What kind of graphs, are there any other graphs people have encountered which naturally, where the vertices break into two classes? Can anybody think of a graph where that's like, yeah?
Matching problems on tests?
Matching problems on tests, right. There are often, when you take the SATs, there's maybe a thing where there are, here are some words, what do you want to call it? Let's say defenestrate and procrastinate. Okay, and then you say the definitions. Procrastinate means, do something late. Defenestrate means what? Does anyone know what defenestrate means? Yeah? Throw somebody out a window, right? Matching, again, but the basic problem there is you've got one thing which are words and one thing that are definitions. And you want to, in principle, the graph is any possible word might be matched to a definition, right? Any other kinds of graphs people can think of that are naturally bipartite? Okay? It's good to smell when a graph is bipartite. Okay? Are trees bipartite? Let's think about it. Okay? If we have a tree, what is a tree? A tree is something that looks sort of like this, right? Ka-chunk, 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 right? Is that bipartite? Yes, and why do we know it's bipartite? Let's say the first color was level node up here was blue. The claim is its children we have no constraints on, except that they can't be blue. So we'll color them red. Once we color that node red, note that the nodes below it, the leaves, have no conflicts with anything that is earlier. There is no reason why we can't color all the nodes on the odd levels blue and all the nodes on the even levels reds. Does everybody see that? How many people see that? How many people don't see it and want me to explain it again? Okay, nobody. Okay? So trees are examples of bipartite graphs. Okay? But there are other bipartite graphs. Notice that this graph would be just as bipartite if we added, let's say, an edge over like this. Right? Does everybody see that this graph is still bipartite because now we have added an edge between a red node and a blue node. Okay? So in general, there is a problem of, given a graph, testing whether it is bipartite, finding the two coloring. Okay? Certain graphs naturally are bipartite, certain ones aren't, and we'd like to, given a graph, tell them apart. Okay? Any questions? Why do we care about it? Well, bipartite graphs are simple, are common in a lot of applications, and they're also simple, and certain algorithmic things work well on bipartite graphs. If we've got a bipartite graph, we want to know about it. So how can we tell whether or not a graph is bipartite? Okay? The basic algorithm should seem just like what I did for my tree. I have a vertex here. If I choose arbitrarily to color that one blue, all of its neighbors had better be colored red. Does everybody see that? When I now look at all the a red vertex, all of its neighbors had better be blue. Does everybody see that? And when I color a blue node, either its neighbors had better be red, or its neighbors had better not yet have a color. Okay? If I try to color this node blue, and this blue was blue, and one of its neighbors was also blue, then that means we found a contradiction and the graph can't be bipartite. Does everybody see what we're doing? We're basically going to take the same idea we did with the tree, okay, and we're going to color our node and color. The point is that once you color one node, the color of its neighbors is forced. And therefore, if we have if when we look at a node of a color, if when we try to color all of its outgoing neighbors, if one of them is colored the wrong color, then we are stuck. We have hit a contradiction, and the graph is not bipartite. Okay? If we hit a node of the other color, well, that's fine. That's what we expect. Okay? But basically, because the colors of neighbors are constrained, and there's only one other choice, the decision of colors is forced, okay, as we go through a walk through the graph. Any questions about that? Okay, how many people understand how we would tell whether a graph is bipartite? Okay, any questions? Now, how do we program a computer to do it? Okay, well, okay, yeah, you tell me. Breadth first search, okay, that was a rhetorical question. But you're right, we use breadth first search, and how do we use breadth first search? Well, the basic algorithm, I want you to look at this two parts, let's say, of a breadth first search based algorithm for something. The first is the wrapper, okay? What are we going to be doing, okay? Basically what we're going to do is we're going to have an external array. For each vertex, what's its color? Initially it is uncolored, okay? And every vertex is uncolored. So vertex I is uncolored. Okay? Initially, as far as we know, the graph is bipartite, so we'll say that bipartite is true. We'll then do a breadth first search starting from the first vertex. Okay? And what are we going to be doing? Well, basically, if this and in general, to deal with different connected components, okay, if the first vertex, the ith vertex, is undiscovered, that was one of those flags from the binary, the BFS, the breadth first search, we're going to color it arbitrarily white. It's the first vertex in a color, the first vertex of our component, we'll color it white. We're then going to do a breadth first search from this vertex and explore all of the edges incident on it. And then once we do that, explore all the vertices incident upon every other vertex. And in the course of it, we're going to walk through every edge twice. Once from the first vertex down to a second, and the other when we explore the second vertex, right? In each case, we go through the adjacency list of the vertex. If it's an undirected graph, we're going to explore the edge coming this way and going that way. We will explore it twice. Okay? So what are we going to do? We want to take an action every time we see a vertex, an edge. What is our goal to do whenever we see an edge? Each edge is going to go from a vertex, of a particular vertex I, to another vertex J. Basically, what do we want to do? Check, is vertex J colored? If vertex J is not colored, then let's color it by giving it the opposite color of vertex I. If vertex J is colored, check to see whether the color of vertex J is different than vertex I. If it's not different, then we have a contradiction and the graph isn't bipartite. Does everybody see that? That's the basic procedure. How do we implement it? Any questions about what the procedure is? That much should be clear. How do you implement it? Well, we're going to be doing basically, I showed you in my breadth first search, I had a place where I called something called process edge. That said, that was one place in the search uniquely where I can say, here is the first time I've seen this edge. And you should program that to do whatever you want it to do. In the case of bipartite testing, what do you want to do? You see, is the color of vertex X the same as vertex Y? Okay, if so, the graph is not bipartite. Okay? Otherwise, they differ. If the colors differ, it could differ in my case because of two reasons. One is that one is red and one is blue. The other is that one is red and the other is uncolored yet. Okay? Either case, so long as the colors are different, I might as well color vertex Y, okay, the opposite color of vertex blue. And so complement color is simply a routine that if I say in is white, okay, return black. If the color is black, return white. Okay? Any questions about that? Does everybody see how adding this piece of code to my breadth-first search traversal does the coloring operation as I go through my graph? Any questions about that? Okay? This is a good example of how we're going to use breadth-first search and depth-first search. There may be some setup outside. We're then going to do a traversal. As we walk through an edge and a vertex, we want to take a particular action knowing this is the first time we have seen that edge. Okay? And in this case, we want to see what's the implication for the coloring. Any questions about bipartite graphs, why they're good things, or more than that, what the mechanics are to do this? Okay? Implement it. Any questions about that? How many people are with me now? Okay, good. Okay? So let's now look a little bit more at one of the properties of breadth. Now, okay, that's now going to catch me up to the end of what was the intended lecture for last time. File, view, full screen, kabunk. Kabunk, 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 boom, boom, boom. Okay, let's look at the problem of the day. And the problem of the day is going to start to get into some of the subtlety of breadth-first search. And more than that, lead us into what's going to be the big subtleties with depth-first search. It says something that says, prove that in a breadth-first search on an undirected graph, that's an important word, every edge is either a tree edge or a cross edge. Where a cross edge is an edge to XY, the edge goes to someone that's neither an ancestor or a descendant. Okay? So let's picture the following. Here we have our graph. This is G. Here we're starting from some vertex. We're going to do a breadth-first search of this thing. What is going to happen in the course of a breadth-first search? We're going to start from some vertex. We're going to explore a neighbor. Go back. Discover a new neighbor. Discover a new neighbor. Does everybody see that? When we go through the next vertex, these discovering new neighbors, we're going to call those edges tree edges. They're the ones that appear in the parent relation. That's the breadth-first search tree. Does everybody see it? Maybe as we explore the outgoing edges, we discover somebody new. We discover somebody new. We discover somebody old. Does everybody see that if this vertex here had a neighbor of this vertex, the time we would have first visited that edge is when we are exploring the neighbors of this. Does everybody see this? There is a discovery period. That's when we pop it in the queue and we point to it with a tree edge. And then there is an explore period, right? Does everybody see that? So this might very well happen. And now we might proceed. Maybe this is going to discover somebody else. There might be some outgoing edges from here. Yes, certainly this edge is going to go back to the other guy. Maybe there is an edge over to here. We explore this particular vertex. Maybe we discover a lot of other guys. The question is it possible, if this is, let's say, our tree of discovery, what other non-tree of discovery edges might there be, and where could they go? Could we have an edge go from a vertex to another previously discovered vertex on the same level? Okay? People see what I mean? This is a non-tree edge. Okay? but that as we explore this vertex, we might have an edge to a neighbor over here. Does everybody see that that might happen? Okay? Might we have an edge from this vertex over to here? Let's think about this. Is that possible? That when we come here, we first, as we explore this vertex, we go, in some sense, first visit this edge when we are expanding that. I want to claim no, we can't. Okay? Why is that? Yeah? Because if you think about how we were doing our traversal, we expanded this vertex before we expanded that one. Does everybody see that? So the first time we would have visited this edge would not have been that way. Let's squiggle this thing out, right? But would have done that way. Does everybody see this? So there's certain constraints we have. The fact that we're doing a breadth-first search gives us some constraints on the nature of a tree. Okay? Is it possible that we could have had an edge that goes from here, let's say, back to an ancestor? Okay? That we first visit this blue edge when we're expanding this vertex. Is that possible in a breadth-first search? I'm hearing no. I'm seeing at least one head shake. Why is that not possible? Okay, yeah?
For the same reason that when we looked at all the adjacent vertices to the one above it, we would have found that the one above.
Does everybody see that this edge, if this edge had really existed in the graph, what would have happened? This vertex wasn't destined to be discovered a long time ago from now. Instead, this vertex would have had a red edge, a tree discovery edge down to there, right? So this is why in a breadth-first search, you can never have an edge go back to an ancestor. Does everybody see that? If we mark an edge as being the first thing that happens to it, each edge is going to be visited twice. An edge might be something that discovers a new vertex and lives in the breadth-first search tree. An edge is not going to go back to a descendant. It's not an ancestor. It's not going to go forward to a descendant. The only place where it can go, actually, is basically over to somebody who's not an ancestor or a descendant. Does everybody kind of get that idea? That by the nature of the breadth-first search thing, you have the probability that when I look at every edge from here, either it's going to go to, if any newly discovered edges, either it might discover a new vertex and be in a tree edge, or it might go back to some discovered but not previously explored vertex. Does everybody see that? So an edge might go like that, an edge might go like this to somebody else, but the only way the edges are going to go, there's nothing going to an ancestor, nothing going to a descendant. It's basically going to, I guess you'd say a cousin, okay? And in fact, it's going to a distantly related cousin. Why? Could you have an edge that goes back, let's say, let's point this thing like this. Could there be an edge from this vertex, let's say, to a cousin 2 levels removed? The answer is no, because if there was an edge like that, this vertex would not have been discovered here. This vertex would have been discovered earlier. Does everybody see that? So what's interesting about breadth-first search is that it, in some sense, lays out the edges in an interesting way. When you finish a breadth-first search, you're going to have a well-defined tree, a tree of discovery, and all the other edges, the first time you're going to see them, are going to be across 2 neighboring levels. Does everybody see that? And never going back up to an ancestor. Yes?
I understand the concept, but how would you write a proof?
Okay, a proof is an explanation. So let me think about it. There are a couple of different ways to think about it, okay? A proof is, in principle, a demonstration, okay? It is supposed to convince, it's an argument that convinces somebody, okay? What does QED mean? Okay, everybody ever write at the end of a proof QED? Quad something something, okay? It means this is demonstrated. That's really what it means. It's Latin for that. So what a proof, as far as, there are philosophical questions of what is a proof. What a proof is an argument demonstrating something, okay? And in this case, my proof is going to be a case analysis, okay? Where I'm going to say, what are the possible places where it can go? Could it go to an ancestor? No, it can't, because that's a contradiction. If it went to an ancestor, it couldn't go to an ancestor, because if the graph was like that, this edge would have been discovered there. Okay? And it can't go to a descendant, because if so, then we would have discovered its parent then. Okay? So the basic proof is it's a systematic enumeration of all the possible cases. And that would be the proof. Okay? Any questions? So to do this right, you've got to carefully write out what all the possible cases are. But you should see right now what the logic is here as to why edges can't go every which way. Okay? It's because of the process of the breadth-first search uses to discover it. Any questions? Does everybody see that breadth-first search lays out, does everybody get this distinction between there are tree edges and there are other edges? Every other edge in the graph is going to get a different label. It's not a tree edge, but where it can go between two nodes in the tree is highly constrained because of the process of breadth-first search. Any questions about that? Okay, good. Okay, any other questions here? Okay, so the reason this is important to have gone through is that our next step is going to be to talk about depth-first search. And there are a couple of different ways to think about depth-first search. One way to think about depth-first search is just to say it's breadth-first search where you use a stack instead of a first-in, first-out queue, okay, to store the nodes that have been discovered and not found and not fully explored. That is depth-first search, okay? And so by that measure, on some ways, there's not really that much of a difference between breadth-first search and depth-first search. Both of them visit every vertex and every edge in the graph efficiently. You could have done my bipartite graph coloring with depth-first search, and it would have worked every bit as good. Okay? Depth-first search is different, though, in two ways. One way important, one way unimportant. The unimportant part is that it's recursive, and so that you can also implement it in a recursive way. I'll show you quickly my recursive implementation. That's the unimportant difference. The important difference is that it orders the edges of the graph in a different way than breadth-first search does. In a way that makes certain algorithms possible. Okay? Any questions about that? So what is my recursive version of depth-first search? Okay? Again, if you think about recursion, recursion is something where a subroutine calls another subroutine and things get nested on a stack, right? If I told you depth-first search was really just like graph traversal using a stack, okay, in some sense, when we do it recursively, we're eliminating the need to explicitly use the stack by using the recursive calls to store what have we partially done so far and need to get back to after we've explored everything else on it. Okay? So what is depth-first search looking like? Basically, again, just like the other one, we're given a graph and a starting vertex. What we're going to want to now basically do is to ask ourselves generally, we're going to start saying if you want to look at a vertex and do something when you visit the vertex first, do it now at the beginning. If not, go through all the edges out from vertex V. That's what this is doing. Look at the adjacency list of V, look at the V element, and start enumerating, going through all edges VY that go out from V. Let's continue. Kabunk. Kabunk. If Y has not been discovered, then congratulations. You have this edge, Vy, has discovered a new vertex. Okay, Vy. Y is now new. It's been discovered. I now get to be the parent of it because I discovered it. I am now going to process that tree edge. This is the first time we've seen that edge. I'm going to do something with it. If you want me to do something on the edge, now you have an opportunity. The difference is now I'm going to start exploring from here instead of waiting until I have processed all the other edges coming out of V. Does everybody see what the difference in depth? Breadth first search, the search radiated out from V. Depth first search, when I discover something new, I jump to it. Sort of like channel surfing or maybe web surfing or something like that, right? Whenever you see something new, you go for it, okay? And we'll eventually have to go and explore all the neighbors of V, okay? But now we're saying save V, call DFS recursively, and now resume the search from Y. And I'm going to look at all the outgoing edges of Y. And if I find that I discover a new vertex, well, that's great. I'm going to now call DFS again and explore from there. So breadth first search was one of radiating and spiraling out. Depth first search is one of the moment I discover something, go there, go there, go there, go there, go there. Nothing to discover, go back. Anything else there, go back, go back. Anything else there, go back. Does everybody see that the shape of the tree is liable to be quite different? By definition, a BFS tree is going to be flat, finding the shortest path from this vertex V, the root, to everybody else. Depth first search is going to try to wander, in some sense, as far from the starting point as it sort of can, before it eventually backs up and picks up whatever else it has missed. Any questions about it? Okay. So what are we going to do? If we discover a new vertex, that's fine. Okay? Put it in the tree, process the edge, and then resume the search. If vertex Y has already been discovered, then the claim is I either may or may not be visiting that edge from V to Y for the first time. There is a certain amount of logic here to try to determine whether or not I am visiting this edge for the first time. Under these conditions, if it is true, then I am going to process that edge. And so every edge will get processed exactly once. And then I'm going to keep going on to the next neighbor of V, the next neighbor until I'm out of neighbors. Then I bomb out of this. And if I want to visit a vertex again later after the search, I have an opportunity, which sometimes is useful in an algorithm. Any questions about what the procedure is? Okay. How much time will this take to depth first search take to visit the graph? It's got n vertices and m edges. How much time is this going to take? Any ideas? Okay. I am going to call this for each vertex. I'm going to go through every outgoing edge of that vertex, meaning it's going to take time proportional to the degree of that vertex within each call of DFS. Each vertex will be visited once. Each edge will be visited twice. The time is going to be n plus m. It's the exact same complexity as breadth first search. Any questions about that? Okay. So let's look at an example here. Okay, just to make a quick little example. Okay, actually, here's an example. Let's just try it. Suppose I start doing a traversal from vertex 1. What's going to happen? I'm going to have my stack. I put 1 on my thing. 1 has been discovered. 1 has now been discovered. I pop it off the stack. Say, what will I visit? Well, I I go through my neighbors of 1. I discover 2. 2 gets pushed on my stack. It's a new vertex. Here I have discovered it. That's my element in my tree. And now I'm going to continue from vertex 2. From vertex 2, I'm going to look at my neighbors. And vertex 2, 3 is undiscovered. I'm going to push now, make a recursive call. And 3 is now my active thing. Okay, and I've gone through that edge. Which neighbors do I have? I have a neighbor to 2, but 2's already been discovered, so I don't want to process that edge again, right? Instead now, 4 has not been discovered yet. So I'm now going to make a recursive call from 4. From 4, I look at my neighbors. 3 has already been discovered, but 5 hasn't. Push 5 down on my stack, and now I've got this as my tree. I look at my neighbors of 5. 5 has a neighbor that is 2. 2 is an ancestor of 5. Okay, but that's not a tree of discovery, right? 1 is a neighbor of 5. 1 is also not a discovery. That's also going to be an edge back to an ancestor. Now I've explored all there is of 5. I bomb out of that recursive call. I've explored all there is of 4. I bomb out of that recursive call. 3, bomb out of that recursive call. 2, bomb out of that recursive call. I'm back in my call for 1. Now, the other edge, when I was interrupted when I went to 2, my other outgoing edge was to 6. That is a tree of discovery. Okay? I now explore 6's outgoing edges. There's nothing there. Back up. Nothing else here. Back up. This is my search. Any questions about that? What is interesting? Yeah, question.
When you first went to 1 at the very beginning,
Yeah.
were you supposed to pop it off the stack?
No, I was not supposed to pop it off the stack. And the proof that I wasn't supposed to pop it off the stack is what stack is there? In some sense, there is no stack, right? It's just a nested calls, right? And basically what happens, I'm exploring vertex 1. When I discover something new, I make another recursive call. And that interrupts what I'm doing and goes up, right? So I shouldn't have popped it off the stack, okay? Any questions here? But what's interesting about this? Does everybody see that assuming we have an undirected graph, okay, we again have a breakdown where we have broken down the vertices. There's certain edges that are going to be tree of discovery edges. There's certain edges that are not involved in discovery. But note that the pattern of them is quite different than with breadth first search. Note here that I have an edge, a vertex from a vertex to its ancestor. Does everybody see that? I have a vertex here, an edge going to its ancestor. In fact, the really important and interesting thing about depth first search is that if I have an undirected graph, all the edges are either going to be tree of discovery edges or going back to ancestors. Okay? The key thing about depth first search, okay, excuse me, okay, let's get bunk, clearing. The key idea here is that it organizes the edges in a different way than breadth first search, but a very precise way. Okay? And again, these edges, these classifications can get a little complicated depending upon whether it's breadth first search or depth first search, and whether the graph is directed or undirected. Okay? There's some details here, and I don't want to get too carried away with it. Let's think about the basic case. And again, you can see that there's if you actually implement it, there's a way to with simple logic, but details you have to get right, based on the state of whether a vertex has been processed or completely processed or not. Okay, and when it's been discovered or not. Okay, there are ways to label which of the possible cases of, is it going back to an ancestor? Is it a tree of discovery edge? Is it going to a cousin? Okay? But let's look right now at the case for undirected graphs. Okay, again, there's a certain amount of detail here you have to be classified. The important thing is, and I guess I don't really have a slide I like here, The important thing is that if we have an undirected graph, every edge in a depth-first search is either going to be a tree of discovery edge, or it is going to go back, first time we see it, it's going to be from a vertex back to an ancestor. Why, if it's an undirected graph, can't we have a situation like this, where we first visit this edge, it's going to go down to a descendant of ours that was already discovered? Can this kind of thing ever happen? Okay, where the edge from 1 to 4 is first visited when we are exploring vertex 1? Is this possible? Let's think about it. If we're doing a depth-first search, I claim the answer is no. Why is that? When we start the vertex 1, assuming vertex 2 was the tree of discovery edge, we immediately jumped to vertex 2 and explored everything that was reachable from there before we bopped back up to 1 to finish up its neighborhood, right? If this was an undirected graph, the edge from 4 to 1 would have been explored when we expanded vertex 4 completely, rather than when we expanded vertex 1 completely. Does everybody see that? So in fact, we would first encounter this edge as a back edge, okay, going back to an ancestor, rather than going down to a descendant. How many people see what I mean by this labeling here? Okay? This is an important property. So it turns out, what can happen in depth-first search? If we have an undirected graph, we can't have edges that we first encounter going to ancestors, going to descendants. We can have them going to ancestors. Could we first encounter them, let's say, going from here to a cousin? Could we possibly have encountered this edge from 3 to 4 when we expanded 3? Okay? Well, if we had done that, note that when we expanded 3, we would have visited all of the outgoing edges from 3 before we explored everything from 2. Does everybody see that? So what would the tree have looked like? We could have had an edge from 3 to 4. That would have been, however, a tree edge. And this edge, okay, would have turned out being used as basically explore. We would have encountered this edge. When we explored 4, it would have gone back to an ancestor then. Do people kind of get this idea? There are constraints on what depth-first search is doing on an undirected graph. And the key point here, if you go through what the possible cases are, every edge is either going to discover a vertex the first time it's around, or it's going to go back to an ancestor. Any questions about that? And this is what makes depth-first search a wonderful thing, is that it organizes the edges of a tree, the edges of a graph, in a very regular way. Everything is either in a tree, the tree of discovery, or goes back to an ancestor. Any questions about that? Okay. Let's see how we can use those kind of properties to design some do some useful things. One thing that's a useful thing in a graph is to find a cycle. Suppose we have a graph where there was a cycle in it. Okay? How would we find a cycle in a graph? Okay? Any ideas? Okay? Yeah?
You try to explore a node and find one that was already explored?
Find a node, and whenever I discover something that's explored, that sort of tells me maybe there's a cycle. But what is that cycle? With a breadth-first search, you could certainly encounter something, and if I just find something that's already been explored, maybe it means something. But let's think about what happens if we do a depth-first search from a node. What's going to happen? We're going to discover something, discover something, discover something. Back up, discover something else. Sometimes, however, we are going to have a back edge. Where does a back edge go? It goes back to my ancestor. Does everybody see that? So if I can tell that this edge did not discover somebody, which is pretty obvious, right? Because the vertex was labeled undiscovered at the time that I visited that vertex, right? What can I say? This vertex has an ancestor who discovered it, discovered it, discovered it. What is my cycle going to be? If I have a back edge, it goes from vertex X to Y. I start from vertex X, keep looking back at my discovered relationship until I hit Y. And the tree edges plus this one back edge is going to be a cycle in the graph. Does everybody see that? There is a cycle. We know that there's a cycle. If there's a back edge, it has to have created a cycle. And that cycle is easily extracted because we know the parents of discovery. Okay? Any questions about that? Now, where is a cycle in a breadth first search? Well, you've got some BFS thing. And now if I have another, what does this be? Maybe I'm going to add another edge. Adding one edge to the tree creates a cycle. But note that this cycle goes up and down, and it's a little more complicated, right? Any questions about how the organization of the depth first search, okay, enables us to look easily for a cycle? Okay? And in fact, it's pretty easy, okay? Whenever we are, we have a thing process edge that looks at each edge for the first time. If, the parent of X, either it was involved in a discovery, in which case the parent of X is going to be Y. If it's not, we found a back edge. If so, where is there going to be a cycle? There's going to be a cycle from, if we have the parent of X, if this is X, the back edge goes to Y. We're going to start from, find the path from Y to the X, okay? And then use this back edge, and that's going to be my cycle. Any questions here? Yes? Can you find all the cycles in a graph? And the answer is, it depends what you mean by all, okay? How many cycles are there in a graph? Let's stop and think about it now, okay? If I give you a graph on n cycles in it, how many cycles might there be? Can anybody, yeah? Does everybody see that? Suppose my graph was a complete graph. I had n vertices and everything was connected to everybody else, right? Now, how many cycles are there in this graph? Okay, the answer is a lot of them. But how many is a lot? Okay? A simple way to count is how many cycles are there visiting exactly n vertices, different vertices along the way. I can start from vertex 1 and go to any other vertex, and then go to any other vertex that I haven't visited, right? There are basically going to be n minus 1 factorial, different cycles of length n. Does everybody see that? So if you ask me, find all the cycles in the graph, list them from beginning 1 to n, 1 to all of them, the number of distinct cycles can be very exponential, right? So if that's what you're asking, that's trouble. We will deal with that trouble when we talk about backtracking. Okay? That's going to be a way of systematically enumerating all of these things. But we should realize there might be a lot of them. Okay? And that's going to be a problem. Okay? What you might be saying is something a little different, which says, take every edge and put it in one cycle. Okay? Let's say that you go and you find a cycle, you pull that one off, and now try to find one cycle, let's say, for every edge. That's something you could use depth first search for. Does that answer your question, or no? Okay, not trying to know the details of it because again, graphs get complicated to think about. But what is the basic picture? If you're allowed to reuse vertices, it should be clear there are an exponential number of different cycles, right? If you're allowed to use each edge only once, since there's only n squared edges, there can't be more than n squared cycles, right? And in fact, and so that would be another way of thinking about it. If you're not allowed to use any vertex more than once, then there can't be more than n cycles, right? So it depends a little bit about what you're asking for. But it should be clear, all possible cycles, exponential, bad, okay? Any questions here? Finding one cycle, depth first search, good, okay? Any questions? Okay, any other questions about finding a cycle? Okay? Again, the thing to recognize is how simple this is once you have depth first search, and to see where you put it in the code to make that happen. It is the only thing about finding a cycle is just a few lines of code added to what do you do when you visit an edge. See what type of edge is it? Is it a back edge or a tree edge? If it's a back edge, you found what you want. Any questions here? Okay. So depth first search is good because it organizes the edges of a graph, okay, in ways that are often, amazingly useful. Okay. Any questions? Let me show you another problem where the organization of the edges into the depth first search thing turns out to be amazingly useful. Okay. And again, with all of these graph problems, there's two levels to think about them. One level is, what is the concept that he's trying to compute? Okay? This is important to know. It's important to understand what are the possible things there are graph algorithms for. Then, once you understand what the concept is, it's good to know how the algorithm works. Okay? So there are a class of problems related to the robustness of a graph. Okay? How many times, are there vertices or edges that are prone to failure? Okay? So suppose, let's say that we had a graph like this, maybe the communications graph of a particular, let's say, city. And let's say you were a terrorist looking for a vertex to blow up. Which vertex will cause the most disruption? Okay? If you blow up this vertex, what's going to happen? Who's going to be concerned? Well, the person who lived there will probably be concerned, but nobody else will particularly care about it, right? On the other hand, what if we blow up this vertex? Does everybody see that if this vertex goes, suddenly there is no way for people here to communicate or drive to any of the people there, right? There was one vertex whose failure disconnected the graph. Does everybody see that? A vertex whose failure will disconnect the graph is called an articulation vertex. That's how we call it. Okay? A related concept, okay, which maybe I'm maybe going to talk about today, just because I think it's actually maybe a little easier, is something of an edge whose deletion will disconnect the graph. Look at this this thing. Notice that there is one edge here whose deletion would disconnect the graph. Okay? If we delete this edge, nobody cares. We delete this edge, on the other hand, we sever connectivity. We call an edge which, if we delete it, okay, will disconnect the graph, a bridge. Does everybody see that? You knock out the Verrazano Bridge, Staten Island is lost, right? There's no other way to get off Staten Island. Well, I guess there is the ferry. Forget the ferry. There's another bridge there, isn't there? There's the outer bridge crossing, right? Okay, and okay. So maybe Staten Island's not in such bad shape. But do you agree that on this map here, there is an edge whose deletion will disconnect the graph? Okay. How can we find? Can anybody think? Again, I think the connectivity issue, the question of how robust is a graph, clearly comes up when you design a communications network. Okay? You want to basically add edges so that your graph has some fault tolerance to it, right? And note that you don't often have to add too many edges to do it. Suppose, let's say, this was the electric network that Lilco runs, or LiPo runs. Okay, any one power line disconnects the graph, right? How would they solve this problem? By adding one more edge, right? And now with only adding one edge, now everybody else is protected, right? There's no way to cut one graph edge anymore and disconnect the thing. Does everybody see that? Okay, so how can we tell whether or not, how can we find if a graph, let's just for the sake of defining it this time, let's talk about, I'm sorry about that, kabunk, get that thing to go away. Get off of me. Go. Okay? Let's think about this problem here, where we want to try to determine whether or not there is an edge whose deletion will disconnect the graph. Suppose I give you n vertices and n edges. I've got n vertices, m edges. How can you tell whether or not a graph contains a bridge? Can anybody give me an algorithm to tell whether there is an edge whose deletion will disconnect the graph? Okay, yes?
Could you see if one vertex only has, or any vertex only has one parent, and therefore that means that it's a bridge that links?
Okay, you're saying if a vertex has only one parent. Now note that one parent doesn't do the job, because everybody only has one parent. If we think of it in terms of a depth-first search tree or a breadth-first search tree, every node has only one parent. So parent is the wrong term. You had something else you were using. You were going to say. And child. You're saying that if a vertex has only one child,
it has a parent and its parent only has one child.
If a vertex has a parent and its parent has only one child, will that cause it to be deletable? Look at this particular graph here. In this particular graph, every vertex has what you would call, I guess, if we did a depth-first search, again, if you keep wanting to use parents, every vertex has only one parent and one child, but you can't delete any of them and disconnect the graph. Do you see that? So the fact that you have one child or one parent doesn't make you vulnerable. Okay? It's a property of the bigger part of the graph. Okay? How many people see that? Okay? How many people don't see that? Okay, question. Okay, so notice that we're trying to figure out, is there an edge that is vulnerable? Let's think in terms of an edge. Here, this is a vulnerable edge. If I delete that edge, the graph breaks into two pieces, right? How can you tell if there is an edge that breaks into two pieces? Okay? One suggestion is, well, if an edge is going to be vulnerable, then probably it's got very few neighbors or something like that. But note that in this particular graph, every vertex has exactly two neighbors. And it's not at all vulnerable. You can take out any edge, and the graph still hangs together. So the degree is not the consideration that we need to worry about. Okay? Yes? Okay, you're saying that it looks like cycles have something to do with invulnerability. I'm sorry about that. See if that'll eventually go away. Good. That cycles seem to have something to do with non-vulnerability. Okay? And that you said, well, maybe this property of going back to an ancestor seemingly is important. Okay? Hold that thought. Okay? Because I want to make sure people understand the dumb way to do it before I show you the smart way to do it, which is that. Yes?
If an edge is part of a loop,
Yes.
then it would be not vulnerable, right?
If an edge is part of a loop, then it is a cycle, then it is not vulnerable. That is certainly true. Okay? If an edge is in a cycle, it won't be vulnerable. Okay? So that would be true. But now I'm trying to figure out, what do you do with that? Okay, we said that there's lots and lots of cycles. If you say, go through all the cycles in the graph, she can explain to you how there's an exponential number of cycles possible in the graph, right? So one algorithm is find all possible cycles, label each edge if it was involved in a cycle, and if not, give up, right? But that's bad because there's an exponential number of cycles, right? What is a simple, straightforward way to test whether an edge will deleting an edge? Yes? Right. Does everybody see that the simple idea is that to tell whether an edge or a vertex is vulnerable, but the idea is, why don't we just delete the vertex or an edge and then test if the remaining graph is connected? How do we test if a graph is connected? If we do a binary, a depth first search or a breadth first search from some vertex, if we visit everybody in the graph on that case, okay, if it's still one component, then the graph, this is not a vulnerable thing. If it used to be connected, meaning you did a depth first search and you visited everything, now you delete an edge or a vertex and the graph is now disconnected, that vertex or edge is vulnerable. How much time does it take to do a depth first search or a breadth first search of a graph with n vertices and m edges? N plus m. If we want to find which edge is vulnerable, we would try that m times, right? One for each edge. You delete it, test it, put it back. That would give you something like m times n plus m. Does everybody agree that that gives you a correct way to do it? The delete and test process is a way to do it. Okay? Any questions? But she gave an idea that seemingly leads to a better, faster way to do it. Okay? By using the organization of the edges because of depth first search. Okay? The way I'd like to think about it is, suppose I took my graph, okay, and did a depth first search on it. Okay? Ka-chunk, ka-chunk, ka-chunk. Okay? There are tree edges here. Note that the tree edges alone hold the graph together. Okay? First thing to note is, if I did a depth first search on the graph, does everybody see that the tree, if I don't delete anything, I delete all the edges but the tree, the graph is going to be connected? Does everybody see that? Why is it that I can delete any edge that's not in the tree and it still be connected? Okay? Why is that? It's because the tree itself is connecting everybody, right? Does everybody see that? So, none of the back edges, again, I'm doing a depth first search, what did I have? I had tree edges and I had edges going back to an ancestor, right? So the tree edges can't be bridges, okay? The back edges, what do? Shoop. Well, I guess I've had them blue. Shoop. I think of the back edge as being this rope that somebody, a mountaineer, is sort of tossing up there, further up to try to hold themselves here. Does everybody see that once you have loaded this rope, you can delete this edge, used to be something that would be disconnected. This edge used to be a bridge. This rope gives you an alternate thing because it's the other edges on the cycle, right? And once this back edge proves that these two edges cannot be bridges, okay? In a tree, basically every edge is a bridge, right? Any edge you put is going to disconnect the tree. But the back edge is what sort of protects it and holds it on, right? So what are we going to do? We're going to do a depth first search, okay? And So long, when we look at it, what's going to happen in the course of a depth-first search? Let's think of what happens in the course of the traversal. Hold on, Kabunk, clear? What is the actual execution of what's going to happen? We're going to go to this vertex, go down, go down, go down, look at the back edge, right? And then back up to this vertex. Remember, like when we were doing like an in-order traversal of a tree? We go down to a vertex. When we finish, we kind of back up to the previous state, right? Suppose we keep track of what was, every edge here went back to an ancestor. Suppose we keep track of the ID number of the ancestor, the oldest ancestor we have reached so far. In this case, this went back to ancestor 1, 2, 3, 4. This edge went back to 4. That basically protects all of these things. Now for this edge, I'm going to want to know, do I go back to an earlier ancestor? Okay? I'm going to traversal down here. This goes back to an earlier ancestor, so this is protected. I keep going down from here now. Discover something, nothing to discover, back up. Note that here I am backing up here without having gone to an earlier ancestor. That means that this edge over here has to be an edge whose deletion will disconnect the graph. Okay? Any questions about that? Okay? The back edges provide ropes. Okay? These mountaineering things. I'm picturing the rope with the the anchor at the other end. You've seen these in the Bond, the James Bond films, right? They hoist it up to try to keep them so when the bad guy cuts the rope that's going to lead him to the death, this is what is going to hold them anchored. It's the back edges that are anchoring them, right? And depth-first search, if you do it like this way, if you think about this, it should be clear this leads to a linear type of algorithm. If you can do the bookkeeping of how far back have I gone so far, okay, what's the oldest ancestor I have, okay? And I claim that that kind of bookkeeping can be done readily, and the details would be in the book. Any questions about that? Does everybody see now how you can tell whether or not a graph is disconnect? An edge will disconnect the graph, and similar logic will deal with whether the deletion of the vertex will disconnect the graph. Okay? Any questions about that? And the only reason this works is because depth-first search has neatly ordered all the edges. They are either in the tree or they go back to an ancestor. Any questions about that? Okay? Any questions? Now, one property of these searches, which I didn't talk about, okay, but maybe I'll talk about now. If you go back to my depth-first search implementation, I did something kind of funny, okay? I had another auxiliary array telling me, I had discovered I already had before. I had a different thing. I had a notion of time. And I had an entry time, which I assigned for each vertex, and a, also a deletion time, an exit time. Okay? So suppose I think of a clock, okay, where I am going to keep track for every vertex of when I first entered it and when I exited it. Let's think about this particular tree. At time 1, I discovered this vertex, right? At time 2, I discovered this vertex. If I'm doing a depth-first search. At a time 3, I discovered this vertex. At a time 4, I discovered that vertex. At a time 5, I left that vertex. Does everybody see that? I went back up to here. We say the leaving time is when I have completely processed that vertex. 6, I went up here. At time here, I went down. And at time 6, I discovered that vertex. And at time 7, I left that vertex to go back up here. At time 8, I finished this vertex. I then went back up here, and at time 9 discovered this. At time 10, I left that. At time 11, I came back up here. Okay? At time 12, well, I started going here, but I get recorded because I then discovered this. 13, I discovered this. 13, I left it. 14, I came back. Does everybody see that if I think about the discovery time as when I first visit a vertex, and the exit time as when I left that vertex forever, I get these kind of times. Okay? How many people see what I mean by these times? How many people don't see what I mean by these times? Any questions? What's an interesting property of these times? Okay? If we, yeah.
Isn't it the post-order pre-order?
It's the same kind of event as happens in a in-order traversal. Okay? Well, okay, I guess it's clear that this is sort of like an in-order traversal because it's a recursive type thing. The thing that is interesting about it is, note that for every node, your finishing time is later than all of your descendants. Does everybody see this? This root was what started first and finished first. First in, last out, right? And for every particular node, if you look at it, every node starts before any of its descendants and finishes after any of its descendants. Does everybody see that? Look at this node here. It started before any of its descendants and finished before any of its descendants. Finished after any of its descendants. Any questions? These times are kind of useful because they sort of organize the vertices into which vertices are older than which other vertices in the search. Okay? And this is another kind of interesting property of depth-first search that we can exploit in a graph. Okay? Any questions about that? Do people see what that property now of what it means entry time and exit time? You may not see what I'm going to do with it, but you should see that it can be computed and that it should have this nesting property in the course of a breadth-first search, depth-first search. Any questions? Okay, keep that thought. When we look now at another algorithm on, important algorithm on graphs. Okay? And this has to do with the problem of topological sorting. Now, so far, all the problems I've talked about, breadth-first search to find shortest path, and finding bridges, and finding connected components, and coloring it bipartite thing, all of those were on undirected graphs. The mother of all problems on directed graphs, okay, is something called topological sorting. Okay? Suppose we have a directed acyclic graph. That acyclic meant no cycles. Here we have a directed acyclic graph. Okay? Note that it's directed. Note that it's not a tree-like thing. It has things that if you ignored the directions of the edges would look like cycles. But in fact, there is no way to go from a vertex back to itself. I can go ka-chunk, 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 but this edge is the wrong way to take me back, right? I can go ka-chunk, but I can't get back, can't get back. Does everybody see this? This graph has the property that it is directed, but it has no directed cycles. It is a directed acyclic graph. Okay? A directed acyclic graph is something we call it, call it often enough, we call it a DAG. Okay? One thing that's an interesting property of a directed acyclic graph is that there is a way to order the vertices from left to right such that all the edges go, okay, according to the order. Note that the vertices here go from A to G. Here I've got A, B, C, D, E, F, G. Every vertex is there, right? If we look at the edges and we sort of draw it on this thing, there is an edge from G to A, right? It goes from left to right. From A to B, it goes from left to right. A to C, it goes from left to right. B to C, left to right. C to D, left to right. There's no C to D, but there is one that's C to E. Okay? F to G. F to E goes left to right. Does everybody see that this order has a special property to it? If I order the vertices, take the vertices of this graph, order them like this, okay? All the edges then point from left to right, okay? Any questions about it? That ordering is something very important that we'll call a topological sort. And this turns out to be the mother of all things you want to do with directed graphs. Okay, directed acyclic graphs. First of all, is it possible to have such an ordering if the graph has a cycle in it, a directed cycle in it? No. Why not? You could go ka-chunk, 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 but if there's a cycle, it's going to want to go back to where it started, right? And the only way it could do that is if there was an edge going from right to left. Does everybody get that idea? Okay? So what is interesting? It is clear that if we have a directed graph with cycles, you can't have such an order. It's not obvious, but will be proven when I get around to it, that if there is a DAG, there always is such an order to it. Okay? And this is an important thing. Okay? Any questions here? What things in life are DAGs? Has anybody ever encountered a DAG? Okay? Why might you have a DAG? Okay? A directed acyclic graph. Is there ever a directed acyclic graph in anybody's life? I think we talked about it a little bit. But you got to come to recognize these things. What in life is a graph that is a DAG? Can anyone describe one? Yes. Course prerequisites, right? The vertices are courses. The edges are, okay, this is a prerequisite to that. Your life, your college transcript is a topological sort of those courses. Isn't that right? Because under no conditions did you take a course after its prerequisite. You never took a course before its prerequisite, right? So if you took your college transcript, tilt it to the side, all the edges go from left to right along prerequisites. Any questions about that? Any other ideas of things that are DAGs or have prerequisites? Okay, but it's kind of a structure of something having to be done before something else. Okay? Has anybody ever encountered such a thing? Yes? Proofs? Well, to a certain extent, proofs have some kind of a logical structure to them, right? If you picture a proof as being made up of a variety of lemmas, okay, it's often the case that to prove this, we are going to use that property. And to prove this thing, we're going to use that property. But what is it possible if I say, I'm going to prove that B is true using A, and I'm going to prove that C is true using B, and prove that A is true using C. You've got some kind of circular logic here, okay? And so, in fact, a proof had better not, had sort of better depend upon things you know are true, or else not. You've got a circular reasoning, right? Anything else that is a DAG, okay? My other example, which I liked from another algorithms book, had to do with the constraint scheduling about getting dressed in the morning, okay? which was that I have various types of clothes. What do I have? I have a shirt. I have socks. I have shoes. I have underwear. I have pants. I have a belt. Are there precedence constraints that certain items have to go on before other ones? Okay? Okay, it had better be the case that I put on my underwear before I put on my pants. Does everybody agree with that? Because things could get ugly, right? Socks or shoes, which goes first? Socks had better be put on before shoes. Shoes or pants, which had better be put on first? Okay, I better put my pants on before my shoes. Belt. Should I put on my belt when? I think I have to put it on before or after I put on my pants? I find it's much easier once I have my pants on. Okay? And my shirt, I don't think there's any real constraints on my shirt as I'm thinking about it. And I guess, when should I do my shirt before? Pants, I think I'll put on my shirt before my pants. Any topological sort of this DAG gives me a possible order to get dressed in the morning. I could put on my underwear and my pants and my belt and my socks and my shoes. Or I could put on my socks and my underwear and my pants and my shoes and my belt. Okay? This gives you something to contemplate while you're over break. Okay? Any questions? Yes?
The belt arrow, does that go the other way?
What?
The belt arrow.
The belt says I am going to put on my belt after put on my pants.
Right, so then
Oh, then it should probably go the other way. Okay, fine. Okay, fair enough. Okay, take care, have a good break, and I will talk to you guys when you get back. Thank you.